Good morning, everyone. Our talk, Threat Intelligence, the Malware Analysis Way, is brought by Felipe Duarte. He's done his electronics engineering and is certified in CEH and GREM. He's a late night Python programmer, really passionate about malware, reverse engineering malware, and sharing knowledge with the InfoSec community. Currently working as a lead cyber threat intelligence analyst at Lumu Technologies. Felipe, um, you can begin your talk.
Okay, hello guys. I'm actually really happy to be with you today. So hope you like what I have prepared for you. And uh, here let's start with the nice part. So the idea of the talk, as was said before, so it's actually to see another way of how we can handle threat intel using malware analysis. What's the actual value? And that is something that I want you to have in mind during the whole talk. So I want you to have that clear picture of why we need malware analysis and how with that skill you can actually get really good, nice results for the threat intel part. Okay, so just a small disclaimer. So all the opinions, everything that is going to be discussed during this talk is my opinion, and it does not represent my employer or any other kind of third party, right? So just in case, this is me. That's my picture. This is me here. So, as I said before, I love to program in Python. I'm that kind of guy that program in the night because I don't know, there are more ideas. And also, I really love, I don't know if you notice my face when I talk about malware, but I am kind of smiling because it's kind of fun. At the end of the day, you see that this thing is very interesting, right? So, and also the other thing I like is share things with you. That's why I'm here. So as I said before, I have some certs, CH, Graham, and also I do have the, Sans coin, the Vital Currency Dictator. And that's not about me. Okay, so let's go directly to the real thing. So here we want to. Sorry, I hear any a noise. I don't know. Can anyone mute the microphone just in case?
Mommy can't help you. You're mine. You're mine.
There's a noise. Sorry. So we're going to start talking about malware analysis. And sometimes when we start talking about this topic, we start talking about assembly and instructions and opcodes and a lot of stuff that is highly technical, right? So it's not easy to handle, to grasp these ideas. And there's one question. So what is your motivation behind understanding those things? So if you are analyzing malware without any real reason, there is no purpose about doing that. So actually, it's kind of you are kind of wasting your time at some point, because you are going to feel that there are a bunch of lines of code, but you don't know where to look for. And that's something that you need to have in mind. Okay, so the first idea, the first thing, always you need to know before starting to analyze a malware sample. What is your motivation? What are you looking for? What is your goal behind the analysis? If you don't know to answer that, so it's better to not start reversing that assembly, those codes, because you are going to get lost, you are going to get bored, you are going to say, okay, that's not something great to do. But that's the idea of this talk, this workshop. So when I talk about malware, I like to have to do like a parallel, a comparison between malware and the cyber world, and just like this is kind of a war actually. So there's a nice quote over there. Sun Tzu said someday, if you know the enemy and know yourself, you need not fear the result of 100 battles. So pretty interesting, because actually the cyber world, the cyber things we have seen this day, actually that's a war, exactly. So there are some bad guys, some good guys, and we are trying to fight this war, trying to survive, actually. So let's think about this cyber war. Let's think about the enemy, right? So I don't know if you have seen Twitter like those days, but there are some very important families, threat actors that are actually using a lot of stuff. So Emotet, every day we receive a fan of Emotet, TrickBot, even though it was attacked during, I don't know, like last month, it has been attacked by the US government. Actually, that botnet is still online. And actually, those attackers are sending like more or creating more tools. They also are related, for example, to real ransomware. So actually, they have their goal in mind. They know what to do. And to have like a more clear picture. So this week, a lot of healthcare and public health sector companies were affected. Again, Treatbug, Bazaar Loader, ransomware, including Ryuk, was seen targeting these sectors especially. So our enemy, they know what they're doing. So the question is, we, as the good guys, as the defenders, as the blue team, we know how to defend ourselves. So what are we doing to do that? And here, because we are talking about a war, we are talking about a strategy, right? So we need to design a strategy, plan a strategy before doing anything. Otherwise, probably it's likely we are going to die in this war. So first strategy that is very used. Actually, this kind of strategy is changing a little bit these days, but it's actually, you can find people that has this scheme of defense or strategy. So I call it the coyote. And basically, it's the same thing. So you have like your Acme mail order catalog with a bunch of fancy tools. And because you have all those tools, you say, no, I don't need to worry about. So things that probably, or ideas that could probably appear in your mind talking about this strategy. So yeah, I have the best antivirus. My EDR is the best. My IDS is the best. My firewall, everything that I have is the best because I paid a lot for that, so I don't need to worry. The other one, so I don't see any attack, so I don't have any attack, and nothing is happening, so I don't need to worry about. And another thing, so I was infected by something. I just removed the threat, and well, everything is done. So let's continue. And that's the thing. So if you remember these cartoons, you will remember that the coyote was always behind the roadrunner, right? So always behind, always chasing, never win. He never actually won anything. So he was just following the tracks that the roadrunner did. And actually, that is something that usually happens with us. So cybersecurity, at least from the defender standpoint of view, is like we are always finding things that the bad guys did, but never we are ahead of them. It's kind of difficult. But we need to remember something. We are not in a cartoon. So we need to implement kind of a new strategy based on real wars, not cartoon fights, right? So that's why I like to think about this guy, Alan Turing. Probably you know a lot about him. He's kind of the father of the computer science. And there was something very interesting about him. And actually, he had a team, and he was part of the Allies. He helped the Allies in the Second World War to crack the cryptographic code of a machine called Enigma. Okay, that there is a movie actually about that. But there was something very interesting because he was part. He took a real part during this war, They didn't work. They didn't have like any guns, but they did something that saved a lot of lives. Around 14 million human lives were saved because they managed to crack the code, and with that, they managed to get information about the attacks the Nazis were trying to execute beforehand. So they were already prepared when the Nazis start attacking. So if we think about this, actually, it makes a lot of sense if we start thinking about this kind of or this point of view about malware, and that's why we can do a comparison. So in the Second World War, there was a machine called Enigma. It was a tool that the bad guys were using to commit their actions, to complete their goals. In our world, there's not an Enigma machine. There are multiple Enigma machines, and they are called malware. And why? First, they're Enigma because, well, they have some protections. There are a lot of stuff going on, these samples, but also they are tools, same thing as Enigma, to commit crime, right? So, okay, there are some interesting comparisons here. But there's an advantage we have in this new cyber world. What's this advantage? Basically, well, if you think about it, when the Allies took the first Enigma machine, I think that wasn't a very simple task. Why? Because Nazis know how important these machines actually were. So they tried to protect them as much as possible because they don't want any other hands touching those things, like trying to hack those things. But if you think about malware, you receive malware every day. So for you to be infected, you need to receive the sample. So the bad guys are sending you the sample. There's a huge difference between both scenarios. And that's an advantage because the fact that you receive a malware actually are those are bad guys telling you, okay, I'm using this. So next time, if you understand everything about that, you can block it. So think about that. Every time you receive something bad, actually the bad guys are giving you everything, all the details. And you need to dig a little bit about on that to get the information we want. So have that in mind. That's something that we would like to see every time you want or you receive a malware sample. So what's the strategy that I propose actually? So first, recollect as much malware as possible. But those things, where can I find malware? First, your spam box. Probably all the things that you are receiving on your spam, probably they are going to be directly rejected by your systems, and you are losing a lot of information that is in there. So if you recollect those, probably you are going to understand how they are attacking you, or at least trying to. Also, there are a bunch of open source tools that can help you with that. So Bazaar CH, for example, Bazaar from Abuse CH, Virustora, the hybrid analysis, Cape Sandbox. There are a bunch of stuff that you can use to capture samples. Then, once you have captured samples, the thing is you need to prioritize. And to do that, you need to understand your business. So depending on your business, you need to prioritize stuff. And so there are some threats that are going to be more likely to affect you than others. So that's something you need to have in mind. But to handle those things, probably you should use ATT&CK. So probably ATT&CK is a framework that allows you to understand a little bit, have more details about each of the threats, and allow you to organize and kind of prioritize which are the ones you want to handle first. So have that in mind. At least for this workshop, we are going to focus on two parts: analyze and automation. So that's why I kind of highlighted this part, but we're going to focus on that. Okay, so but just in case, these are two parts of the whole chain. And the last one is the improvement. So once you have completed one cycle, you need to learn about the things you have done. So you need to see probably if there is any other kind of source that you can use. If probably a sample that didn't have as much priority as you previously thought, probably you need to increase it or decrease it. I don't know. Or probably you need to speed up your analysis. So you need to change some things during the analysis. And about the automation, every automation probably has bugs. So probably you need to do some changes. So this is the strategy I propose. We are going to focus especially in this workshop in the analysis and automation. And having that in mind, having that clear, so we're going to move directly to a virtual machine and start playing with malware, okay? So we are going directly to this part, which is the most interesting part to the workshop, or about the workshop. Well, so we are going to imagine we are in an incident response. We have received just a suspicious file. I don't know, anyone found, or the forensics team, I don't know, they found something. We have a file there. We don't know what that file does. So we are going to start our investigation on that. We have file, we don't know what it is. So if you downloaded the machine, so you will have that suspicious zip file. Just right click and go to extract files. Extract here, I think. Password is the by default, right? So the standard, the industry standard for malware. So which is infected. All lowercase, infected, right? So if you are going to start, just do it. Perfect. So we have a suspicious exe, so that's interesting, and that's it. I usually, when I start analyzing malware, I have kind of checklist. And that's something that allows me to speed up my analysis. Okay, so I have this checklist here. It contains like 6 bullets. First, they are some simple questions, but they can help you to focus your analysis. So first, the first question I always do is this file packet? Why? Because as I told you previously, the bad guys knows that they are providing you the whole source code. Well, it is not like the actual source code, but they are providing you a low level representation of the source code. So if they don't protect their source code, well, everybody is gonna understand what they are doing. So they try to add stuff just like the matryoshkas. Yes, this small figures that contain one inside the other, inside the other, inside the other. Those layers of protections, malware uses something like that. And those are the packers. And the first thing you need to address, you need to fight during a malware analysis is actually find the packer, try to avoid the packer, and actually get the final payload. And that's something tricky. And we need to understand probably some methods to handle this. So we are going to do 2 different methods to try to find if a sample is packed, and then we can go like deeper to doing a more detailed analysis. Like one is if you are really in a hurry and you need to unpack something really, really fast, and the other with more detail, right? So you have more time. So the first thing I always do while I am trying to detect if a sample is packed or not is use this tool that is Detect Easy. Okay, so Detect Easy basically it parse the B file, and it provides you some information about the library, the linker, if it was compiled using C++, .NET, stuff like that. Also information about the resources, and also information about the entropy. Entropy is a nice indicator. So if you go exactly to entropy, you will see here that there is a bunch of stuff with a really high entropy. When I say high entropy, is the highest value for entropy is 8. Okay. When I say entropy, when we're talking about entropy of a file, basically we are saying how random a piece of the data is. And if you stop to think about it, every time you create a program and you want to understand the program, to try to create a program that does not have a lot of entropy. Otherwise, you are not going to understand anything the next time you see the program. So when you see something with high entropy, could be an indicator that it is packed. And actually, the Detect Easy tells you here, okay, it's probably this thing is packed. Okay, first indicator, but you cannot always rely on your tools, on only your one tool. You need to look other tools just in case, okay? So first thing I see to try to solve the first question, it is packed. I try to see the entropy. Well, based on the entropy, I can say, okay, this thing probably is packed. The other thing that I try to do is kind of a correlation between what I see during the static analysis, a very basic static analysis using strings, and the library, the imports of the file, and the actual behavior. So how can we do that? So I use this PStudio. So we go directly to PStudio, and we're going to load the suspicious exe. So at this point, this is just a static analysis. We are not doing anything pretty sophisticated. We are just looking around, trying to grasp some ideas. So that's the main goal. So why I always use I go first to strings, because recollect, let's suppose you are writing a program that you want that program to connect to an URL. So at some point you need to write the URL. Otherwise, it won't connect, right? So if you don't see any kind of URL here, probably you think, no, it won't connect to anything. But if you see that at the end of the day, after you execute it, it connected to something. So there is a mismatch between what you see during the static versus what you saw during the dynamic analysis. So that kind of contrast allows you to determine very quickly that actually the sample is packed. So yeah, I'm just going to look one piece of advice, guys. Every time you start doing this analysis, don't get too like crazy trying to understand everything. I think that one of the best skills that or the greatest skills that a malware analyst should develop is try to filter information. Try to find among all the information that you see, what is the actual, the real information or the information with the greatest value. And that's something that experience is going to provide you. But that's something you need to have in mind. Not everything that you see is you cannot create like a conspiracy theory about everything. No, you need to try to filter. So that's why I just start like reading this very quick. So when I see this, I am not going to start analyzing everything that you see here. I'm going to say, okay, probably this, according to these strings, this thing has something to do with database. Okay, so those strings says, okay, something about database. This weird string, I don't know what could be, but database. It talks about password, username, admin. Okay, let's leave that in your head. There is a weird name, actually for a binary here. I don't know why. And let's continue. Let's dig. So you see like labels, panels, like probably this could have an interface, for example, and everything, all of this could be a valid string for a .NET file with an interface. So we need to contrast if actually this binary has an interface, for example. But let's continue. Let's continue. So it talks about forms, okay, XML, I don't know. Really, really, really quick. We don't want to spend a lot of time here, just to grasp the main idea. And that's something you need to have in mind. Grasp the main idea. Try to look for URLs, try to look for IPs, probably strings such as I don't know, usernames, user agents, I don't know, like get, post, stuff like that is actually very useful. But at this point, I don't see any of those. Okay, so because I don't see any of those, just kind of garbage. So I am starting to think, okay, this is kind of weird because I only saw stuff related to database, garbage, blah, 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 nothing really important. And that's it. So at the end of our static analysis, what is our conclusion? Well, a lot of garbage and database-related strings. Okay, that's my conclusion. About the imports, I cannot say anything because it is a .NET file. Because it is a .NET file, it only uses one. So I cannot determine any other import. So have that in mind. Now we are going to stop our static analysis, and we are going to execute the file and going to do the comparison. So when I try to execute the file, so just I'm going to open this process monitor. I'm going to leave it there. I think probably you are familiar with it. I'm going to open Process Hacker just in case. So it is here. Perfect. So, and again, I'm just going to execute. The first question I want to solve is, it is packed. That's it, nothing more. So I'm going to execute. Everything is kind of being monitored. I'm going to leave it, just it is. And let's wait what happened. So wait some minutes, probably some malware like have an sleep function there, and it will sleep some seconds, some minutes until it actually does something bad. But we need just to monitor, and actually that's fine. That's something interesting. You double click, you just wait, see what's going on, what happened, and we need just to think, okay, well, we saw something there, something happened, but we don't know what happened. Well, so we are going to do something, and we're now going to analyze first the memory strings of that sample, nothing more. I'm not going to unpack at this point. I'm just trying to solve the question. And we are going to compare what we saw during the static analysis with what we see in the memory strings. So remember, in the static analysis was like database-related strings and a lot of garbage. In memory, what we find: close camera, open camera. Okay, they start. Keep alive, enable, timeout. So we didn't find any kind of that kind of data on the disk. So something changed. There is something. Okay, so if you see like uploading file to C2C, so there is something. There are a lot of strings here that we didn't saw on disk. So this file is actually packed. There is a layer here, and we need to get rid of that. So at least with what we know, we answer the first question. Is packed? Yes, it is packed. Absolutely. Nothing more about the analysis at this point. So now the problem is, well, how can I unpack the sample? Two methods, okay? So I'm going to pause this here. So this is, yeah, I'm going to pause this. So I'm not getting more information. I'm going to leave the sample running. It's running at this point. So what I'm going to do is, if let's suppose I'm in a hurry, I don't want to understand the packer. So what should I do? For example, I added to your console. So if you go to CMD, there is a command called PD. PD basically, well, it stands for process dump. And you can find that code in here, so you can find the URL. But what we are going to do is we are going to dump everything, all the executables that are located in this process, and we are going to see if actually we can catch the unpacked sample. That's it. So what I'm going to do is very simple, nothing really sophisticated. PD dash PID and the process ID, actually, which in this case is 2152. So we're going to do that. It will be PD. Let's do that in desktop. Okay. So we're going to do PD dash PID and the ID that we have for that process, the suspicious process. So, okay. This thing actually created a lot of files here, and there are some. There is one very interesting, which is this. The first thing that I noticed, and I think that's why it captured my attention, is because it has an icon. So why an application, which the original icon was this, like a Google Chrome stuff, why I ended up with another application that has another icon. So weird stuff, right? So that's why there's something going on, and I would like to analyze this. And because I consider this is probably the unpacked sample, so I'm going to do the static analysis. I'm not going to do anything else. And static analysis, I'm going directly to strings just to see and to compare if actually we get something at this point. And this is actually the unpacked sample. So you can get, there are a lot of strings. You can see like stop audio, resume audio, pause audio. Okay, this thing probably like kind of gets a lot of information from the victim. For example, let's go dig more. Okay, yeah. So watch.mutex, rencos mutex, eng. So we have a lot of interesting stuff here. So I think this, if you are in a hurry, this is probably something that can help you to unpack a sample. Very simple. Probably the unpacked sample will be broken because you didn't do any kind of fix, or didn't fix the import tables and a lot of stuff there. But at least if you want to triage really simple, really fast, this could be a very nice solution. So have that in mind. And something that really like is clear. So there's a name, Rencos, directly, Rencos mutex, Rencos. So just for the sake of researching, so we are going just to we're going to look for Rencos on the wild, Rencos rat. Well, Rencos rat, actually that's the name. And actually it's a remote access Trojan. So at least at this point, if you are doing an incident response very quickly, you do know which is the malware that was affecting. You don't need to do like any more kind of reversing about their functionalities because you have a website that has everything. And actually you can buy it or download the free version. They have two, like free and professional. So you don't need to get like really crazy about trying to understand everything because you already have a lot of information here. Okay, but at least we know which was the attack. So really simple, nothing really sophisticated, and this could be a very useful way to unpack a sample if you don't have time, or at least you are starting in this field, okay? That is kind of pro tip number one, and this was the first tool I used to unpack sample, because at the beginning is really, really hard. So we're going to leave this here, and we are going to attack this problem using another technique. So first, we know the sample was packed, and we found a way to unpack it really simple. Okay. Now we are going to be a little bit more detailed about this process. So remember that when I run the sample, I open up this process monitor console, and there is one functionality that is really nice, which is the process tree. If you go to the process tree, you can see how the process's behavior during or over time. And that's something that gives you a lot of idea of what is going on. So the first sample we analyzed was suspicious.exe. Look, it started at some point. So this is the green line is kind of the lifespan. So how long the process was enabled or was active in memory. But in this case, so we have the suspicious.exe. Great. So it started, or remain active some time, and then it was like then there was a SCH task, something with, like, there's a command here. So okay, good. So there was a task that was created. Interesting. Then a console was invoked, so there was like something weird there, and then a new suspicious exe file happened or appear. I don't know. So weird. So what could be going on? Every time you see something like this, like there was a process, then a new process spawned or appear, and then the first process like was completely removed. So the first thing you should think about is about process injection, and don't think about all the details, the technical details, the APIs that were used to do this. Think about the graphic. So just like the plot. It's like, okay, there was a process. It was alive sometime. Then another process started. That new process is the one that continues, and the previous one died. So this is very very common in process injection. In this case, it's not so sophisticated because it injected code in the same binary. So it created a new instance of the same binary and then injected code there. But you will see that there is some malware that doesn't start the same process. It starts explorer.exe, it starts SVC host, for example, so they can change that. But because we know this is Process Explorer, so we need to investigate a little bit what kind of methodology was used about this Process Explorer. So there is one very nice resource, which is the Mitre Navigator. And actually, I really like it because, well, I know there are a lot of usages for this Mitre attack matrix. There are a lot of usages, but for me, at least from the malware analysis and a standpoint of view, like it's very interesting because it's kind of an encyclopedia, dictionary, in which there are a lot of techniques that you can get information about. So we know that probably there was something related with process injection. So we need to find something about that. So privilege escalation, there is something about process injection. So we go there. And you are going to see a lot of techniques. And that's why I consider super, super nice to have all that information in one place. You don't need to get crazy starting look for a lot of blog posts about this. Now everything is here in the matrix, so it's super nice. To be in like we can start like reading a lot of all of those, but to make this like easier, so I already know this is a process hollowing. I think I will start analyzing that because this is very common. Okay, so at least for rats such as that, it is very common to find a process hollowing. So we're going just to view the technique. So we go to the technique, and that's why it's very, very useful to use the matrix, because you are going to find here like the main points of how this thing works. And which is more interesting for me is basically to get an idea about which were the API calls that were used. So create process was one, unmap view of section was another one, virtual unlock EX another one, write process memory was the other one, and that's it. So why this is important? Because at this point I know which are the APIs that I need to monitor. So I can set a breakpoint in each of those, and I can validate if actually this is process injection. So for the sake of like speed, we are going just to focus on two things. So we're going to focus on create process and write process memory. So create process is the one that creates the new process actually. This unmap section view is the one that like removes all the code that was in that process. Something that is important, the process is created like in suspended mode, so it started, but it was like, okay, waiting. Then the malware removes all the code that was loaded by Windows, then allocates a new section of memory, then write the new code inside that section, set the new thread, basically to tell me the software to start the malicious code, and then it resumes the thread to continue the execution of the malicious code. So that's kind of the flow of this injection. But for the sake of speed, we're going just to focus on create process and write process memory, okay? Just to see this working. Again, for this case, we are going to take more time, but we're going to extract more information. So what we're going to do is just like load the binary. Yeah, sorry. So it's because it is a 32 bits binary, so we're going to use the X32DBG, and we're going to send here the binary. That's it. So we are at this point. So we are going to go with this. With this, we're going to go to the entry point. And because we know which are the APIs, so we are going to add some breakpoints. So we're going to add one breakpoint at write process memory. Write process memory. Okay, good. Boom. The other one that I remember is the create process. There are like some variations, so I'm going to use create process A. Boom, and create process W. Boom. So we have at this point the APIs that we are most like interested about. So create process A and W, and the other one which is write process memory. So we're going to start and continue. So there's an exception here. Wait. When there is an exception, what I do so those exceptions in the debugger here are basically that there was like in the order those sections are handled if you're debugging application, and there is an exception. The exceptions are handled first by the debugger. So to skip those things, so you press Shift and F9. With that, you are telling the debugger not to break on the exceptions and continue. Let the program handle its own exceptions. So I just let the program work for a little bit and wait. Perfect. Create process W. So wait, I'm going to finish this one just in case. Okay. Create process W. So there is a new process that is going to be created. Very interesting. With this parameter, I don't know, but this is where it's very, very useful to just find the documentation of this API just to get more information. So I'm going to look for create process W is here. So we're going to, it doesn't matter if it is A or W, that only change the, if it is white or an ASCII-like function, but the functionality is the same. About the create process, one of the most important parts is the creation flags. And when you go here to the creation flags, creation flags, here you can find the process creation flags. The process creation flags, according to what we saw in the process injection, they need to create a process in a suspended mode. Otherwise, it won't work. So we're going to look for the suspended flag, which is 4. So going back to the virtual machine, actually here in the stack, you will see that one parameters is 4. So that means they are going to create the process in a suspended mode. So, well, this seems to be a process injection. So because I just got the idea, okay, this is probably going in the same path that I thought, I'm just going to continue and see that this thing is going to write process memory. So something very interesting. Look that there is a new child process, and actually this color means it is suspended. So yeah, it is going something weird, something obscure is going on here. So at this point, because we are at the point in which the malware is trying to inject the new code. So again, we're going to go to the documentation, and we're going to see what Windows or Microsoft says about write process memory. So write process memory. Well, about write process memory, so there are some interesting things. So first, it needs a handle for the process. It needs the base address in which it will write the information, and the buffer. So the buffer is the actual piece of data that will be written. So having that in mind, again, first is the handle. Second is the address. Third is the buffer. What a handle means, so how can I see if actually we are going to write in the process that we are interested? So basically, if you go to this, to the binary properties and go to handles, we just need to find the handle that is in here, which is 4b4. So let's look for 4b4 here. So there is the handle for this, in which the process handle in which we are going to write is suspicious.exe, and its PID is 6060, which is actually this one. So yeah, we are in the right path. The second thing that we saw, we are going to write in that process at address 450. Okay, and what we are going to write actually is the information that is located in this buffer. So we just click here and say, okay, follow leaverage in dump. And any one of you that recognize this is going to be happy, because yeah, we have found a new binary. And that's kind of the unpacking thing. So we need just to stop the execution in the exact place just to get the most relevant information, trying to avoid all the code that doesn't give us any kind of useful data, okay, just in case. So what I'm going to do is just like right click, go to a memory map, and I'm going to dump that that memory. So dump memory to file, desktop, and we are going to get that memory. So this is the memory section. Found a new binary. So what we're gonna do now. So I want to open this in an X editor just to see if the whole thing was a binary, or if actually it contains another stuff. And actually you see that, yeah, it has a lot of things here. We know the binary is here, but there are a lot of stuff. So we need to find the binary. So I added in the machine for you a data carving tool called Foremost. Probably you are familiar with forensics. You know about Foremost. So Foremost basically it tried to look for the headers of the files, and if it finds like a known header, so it will extract that kind of file. So what we're going to do is just like foremost -t, and we're going to send like the file, and we're going to enter. Boom. So that's it. We got a new folder. In this new folder, we're going to find some pictures, okay, and some exes. So in that memory section that we extracted, there are two exes. The first one was the one, if you remember, if you recall correctly, the first one had the has the same icon than the one we extracted directly from the memory of the previous process. So for me, that is Renko's packet. And the other one is another interesting thing that is going on there. So probably you will say, well, but you didn't fix any kind of imports at this point. So the EIT, the IAT, yeah, the import address table is broken. But for this specific packer, no. This is the actual packet code. And why is that? Because if you see, when they're calling write process memory, they are not copying everything. They are just copying a small piece, which it has a size of 1,000. So what means that? They are starting to copy pieces by pieces. They are loading. They needed to implement the same Windows loader, but in their packer. So the file that we have here is like a regular file, but they need to map that file to memory. So because we are doing that previously to map the file into memory, we have a working copy. So that works at least for this. Okay, just in case, have that in mind. But there is something important. So we know that we have here a Rencos, but we got another binary that we didn't extract. So remember, so this is the Rencos that we extract now. This was the one that we extracted from memory. This one, we don't know anything about it. So we're going to leave this at this point, and we're going just to continue with this small analysis very quickly. So that it's easy just to see what this thing was doing. It is a .NET file. Okay, really interesting. So when I want to analyze a .NET file, so I usually do analyze that using DNSPy. And I just need to do this. So it says Lazarus. Okay, but I want to see what's going on here. So what are like the functions? But these guys never like give us everything for free or easy. So you see like this thing is kind of obfuscated. It's kind of weird. We cannot understand that very simple. So what we are going to do is we are going to close, and there is a tool called D, like deobfuscation for like deobfuscation for .NET, something like that, kind of for you to remember. And I just need to pass that sample and enter. So it detected an obfuscator and it created just this, we get the clean copy. It is this one. So we are going with this clean copy, we are going to open up again dnspy. Let's remove this just in case. Remove Lazarus. And we're going here with the clean one, okay? Just to get an idea, okay, well, what was this thing about? And well, so you see here, okay, it is clean. It is clean now. Probably we are going just to analyze it very simple. For example, this part. You see sandbox, malware, sandbox, virus. I don't know. Is for example this DLL file .exe current user. All those things. This basically is an anti-sandboxing code. So if you probably if the name of this file contains malware, so probably it won't run. That's why sometimes when I try to analyze a sample, I like add a random name just in case. For example, this is another code just focus on VirtualBox, guest additions, VMware. So this is the anti-VM code, for example. We do know that. So if you, for example, want to create a more robust virtual machine, so please learn about what things they are implementing here, what are the kind of security controls they are implementing in their malware to avoid your machine. And if you can change those, so you are good to go. So that's another thing very interesting here. We can go directly, don't remember, yeah, it's this one. You can go directly to this code and you will find first, remember that when we run the process, there was a task. Yeah, this was the file that create that new task. Basically, actually, if you see here, it can download files. So interesting. If you see here, thread contents, read process memory, write process memory, unmap view of section, virtual log ex, resume thread. This is the process following APIs. And actually, this is the code that does that. So it creates the process, it gets the thread context, everything, all of that is going here. Okay, so yeah, this is like at this point we know that there are two stages. So we have the packer. The packer unpacks another .NET file. This file is the one that is in charge of creating the process following, and also verifying that the machine doesn't have any kind of sandbox structure or information related to virtual machines. So interesting. That is kind of the analysis I'm going to do with this sample, but that's not the main topic. But this is how you could analyze very easily .NET files. Okay, so we solve the issue with the .NET files, ready to go. We solve the issue with the malware. We know what malware is. So at this point, we have solved this. Done. How can I unpack it? At least for this sample, you do know how to unpack it. Now, the next part is the part in which we actually going to do some reversing. And because we're going to do some reversing, you need to remember, we don't want to focus on the whole file, because you are going to find a bunch of lines of code, I don't know, like thousands, And if you don't know what you are looking for, so you are going to be lost. So we need to find the most interesting part of the file. And this is the third question. Which is the most interesting part? Which is the thing that I can handle now? So, or which is the part that I will focus on at this point to understand? So we have here the sample. Packet, we are going to do just a basic static analysis in IDA, nothing really sophisticated. We are going just to look for the strings, okay? So we loaded the sample in IDA. I added here the IDA free, so it works. If you want to get more details about the file, probably, and you have the resources, probably you can get the IDA Pro, which allows you to decompile actually the code. It's one option, or there is another option which is Hydra. It has a great decompiler, but at least for me, I'm so get used to the interface of IDA that sometimes it's kind of hard to change to Hydra. But it depends on you. Both things can help you for the same task. So what I'm going to do is just look for strings. So how did I did that? So the command is Shift and F12. So Shift F12, and you're going to see the whole list of strings. And we're going to focus on a specific part. So now let's think about, or let's think how as a programmer, okay? So one of the nice methodologies of the recommended methodologies if you develop software is basically try to reuse as much code as possible. So that's why things such as inheritance exist. There are a bunch of things there that allows you to reuse your code, right? So now, if you want to create a malware, so let's think as threat actors. I want to create a malware, but I want to reuse as much code as possible. I don't want to create the whole attack every time if I want just to change the C2 server. So they are going to maintain the main structure of the file like clean, but they are going to allow an easy access to the settings or the configurations of the attack, just to change very simple. You just change something in the builder, and it will create a new sample with the same code structure but with a new configuration. So with that, they are reusing as much code, and they are like very if they deploy an attack and the server was down, okay, they just create a new server, boom, nothing really, just 2 clicks and that's it. So we need to find that part. That is a very important part during the analysis. Actually, like a pro tip, 2 things that you should focus on. So first one, configurations. So which are the most interesting parts? Configurations. And the second one is, for me, actually, I love that part, is the network protocol, the way the bot speaks with the C2 server. Okay, and network protocols. Well, this could change depending on the kind of malware, because we know this is a rat. We are not going to start looking for encryption algorithms, for example, to the encryption algorithm for files. No. We want just to find the way the configuration is stored, if there is any algorithm going on there in that logic. But for example, if you are fighting with a ransomware, it could be useful to know if it is, for example, if it is using what is the algorithm used to encrypt the files, because if it is a symmetric algorithm, probably it has there the key, and you don't need to do anything sophisticated, just dump the key and get your files back. But for example, if it does implement something like RCA. So okay, you know, probably this thing, we could get the actual files back. But so depending on the sample, you are going to find some parts more interesting than others. At least for rats, configurations and the network protocols are very interesting. And also for botnets could be very, very, very useful, just in case. So, well, now because we know which are the parts more interesting, we need to find how the sample handle the configurations. So looking at the strings, actually, let's start looking at the strings of the unpacked sample. You are going to see directly here in this part that it has keylogger. And actually, this kind of mapping is very used in keyloggers. So, okay, yes, it has keylogger. It can steal data from web browsers. So, very simple. Let's continue. And there is something that is called settings. There is a string called settings. And we were talking about configurations and settings. Well, that's the same thing anyway. So let's see what thing is going on here. So I just double click settings and I went to the actual string and press X. So I'm going to see the X reference and I'm going to press OK. If you see here, you will see that settings is related, or in the code is related to some APIs, which are find resource, load resource, dot resource, site of resource. So that means the settings are a resource in the sample. So if we go to the resource hacker and you go to RC data, you will see that here you have settings. Yeah, and settings is kind of a weird data here. So probably here is the configuration. Probably the configuration is here in an encrypted way. But because I want to focus my analysis at this point just in the configuration, this is the part. My main goal, at least for this reversing, is try to read this. I want to get the information about this. Okay. So how I'm going to do that? Well, I do know when that happened. So I'm just going to rename that. I'm going to say, okay, resource config. Any name you want. I always use like malware MW here just to find in a faster way the functions here. So I only press MW and I know which functions I already like reverse it. Okay. And as I told you, I don't need to reverse everything, just the part that I am most interested on. So because I know which is the part that has that, so I'm going to go back a little bit. So I'm going to see which code calls this part. So I'm going to use cross-reference for this new function that I found. And I found this huge thing. Wait. So there is a huge stuff in here, like a lot of it. So we know that this code got the resources. Okay, so we know that the data that was obtained is this. So, and this is not a valid resource, yeah, a valid configuration. So we need an IP or a C2 server, something. We need something at least that the sample could use to connect. So following the same developer logic, if you have something encrypted and you call it in your software, the only way to use it is decrypted, right? So we need to see what information or what functions are called after the resource. Sorry, here are resources with C. I need to find the piece of code that was called after the resource was loaded to see what was the algorithm implemented just to decrypt this stuff. And that bring us to the fourth part, which is which algorithms does it use. Why is good to focus on algorithms? Because if you detect which is the algorithm, there are some libraries in other languages, such as Python, Go, whatever, that allows you to easily create scripts to extract the data. Otherwise, you need to reverse the whole thing and build the whole logic in another language, and you are going to waste time. So take that into account. So you need to look for algorithms. So we are going to see which functions are going to be called. We are not focused on this because I already found those calls, and those are like standards. We are going to be focused on the calls that doesn't have like this color, the magenta color, no. So the pink color, we don't want those. We want the ones that are in blue. Those are the functions that the developer, the threat actor, created. So we are going to see there are two functions, one in here, the other in here, nothing more. Okay. We see that at this point, I haven't analyzed everything that has been going, that is going on here. I'm not like crazy saying, no, EAX and ECX and whatever. No, I'm just like focused on the functions, main picture, nothing more. I'm just trying to understand the main picture, and then I can focus on the stuff that I really interested. So I just click in the first function, double click. We have that function here. Actually, if you see, it's kind of a wrapper because it receives some arguments, and those arguments are pushed again to a new function and return. So there is not a logic, a real logic here. It's kind of a wrapper. So let's wait. What is the actual function that gets called? And it's this one. This is the function that was called at the end. Okay, so this does something here at the. If you see here, this is kind of a loop. Okay, here there is another loop with some like movements. But wait, so this is where we actually going to reverse, but with a base knowledge of what we are doing. So first, see that this value, which is 266, is moved to EDI, and see that here there is a comparison. So this loop actually is doing a comparison with 256, and it's doing a loop. It starts from EAX, which at this point was 0. So what this does here is just like EAX equals 0. Boom. This part is EAX equals 0. What we are doing here is just like a loop in which in the first position, we are adding 0. Okay, we increment, we start with 0, first position is 0, we increment 1, move to the next position in the array, then compare if we get up to 256. If no, we continue, so the next time is 1. So we are creating an array which the first item is 0, the second is 1, the third is 2, and so on until we get to 256, 55, since 56 will be skipped. So that thing, this picture, so focus on this picture, that picture is actually RC4. And if you go to RC4, in cryptography, RC4, look, if you know the algorithms, you can find this kind of correlations. So the first thing that the key scheduling algorithm of RC4 does is an array from 0 to 255 in which the first item in the array is 0, the second is 1, so on, up to 255. Then there are there is another loop again up to 255, and there are going to be some movements over there. So I don't want to reverse the whole thing. I just want to get an idea. So if I go back here, I see that again, this comparison here is again with 80. So there are two loops that are going to count between 0 to 255. So this is probably most likely to be malware RC4 key scheduling algorithm. Boom, that's it. Nothing more. I don't need to understand anything else because this has the same structure. So I go back a little bit. As I told you, this is a wrapper. So the wrapper basically, I'm going to call it, is this is wrapper. Then I move back, sorry, I move back where I didn't want. Okay, good. So we're at the point in which we are, so we already identified the first instruction here. So continuing with the logic, understanding the algorithm, we can see what happens. So let's read a little bit about here. First, about the RC4. First, it creates an array. It does some changes between values there. Then it does an XOR. The XOR is the actual part that decrypts the data. So according to that, the following call should be like the loop in which RC4 does its XOR function. So we're going to go here. Look that this is also like a wrapper. So we get something here. This is kind of a wrapper. There are a lot of functions, but in the middle, there is another one. But there is not like a lot of branches. There is just one. So this seems more like a wrapper. If we go here exactly to the new function, we are going to see that there is a new loop and there is an XOR. So because there is an XOR, there is a loop, it is most likely to be the actual RC4 decrypt stuff. So we're going to call it malware RC4 decrypt. And that's it. We go back, and this is the wrapper. So malware RC4 decrypt, and this is the wrapper. Well, perfect. Go back. Actually, if you see, for example, at this point, we already identify some algorithms. If you want to reverse more the sample or go deep into the sample, you can cross-reference and see that there is a lot of places in which that wrapper will be used. So probably this can be used to encrypt the data as well. The network traffic data could be encrypted with RC4. I don't know, we need just to find that. But at least in the reversing portion, that part, we already have identified a lot of information. So yes, which algorithm does this thing use? We already know that this thing uses RC4. Okay, perfect. So we address the problem of analyzing malware from like going from something that didn't know what was doing in our infrastructure. We know that it's a remote access Trojan. Its name is Rencos. It was packed. We unpacked it. The most interesting part we found that at this point is the configuration. We know that for that configuration, it uses RC4. So now we have only two questions left. How can I detect the sample? And what kind of things I could automate, okay? Just for the sake of speed. So about the part of detection. So how can I detect malware? So there is something very, very interesting, which is called Jara. Jara, I think it is also installed. So Jara, you have Jara here. Jara have some nice stuff, nice options. At least you can, inside the machine, you can, well, look for samples that contains a specific pattern. It could be a strings pattern, or also could be like an hexadecimal pattern. So one thing. The other, you can analyze files with those rules. Also, you can analyze the memory, the processes that are running in memory. That is another option. So, and the last part, you can scan, for example, using volatility. You can scan a whole memory dump of an infected machine using your Jara rules. So that's why Jara is very handy, very useful. Just have that in mind. So we are going to write a very simple Jara rule. So it's going to be rule, and we're going to call it rank cost. Okay, got it. So it has some fields. So for example, the first field is like metadata, but I'm not going to write anything there. So we can go into with two parts. So the first one, the most important ones are the condition and the strings. So the strings, as I told you, the strings could be actual strings. So the ones that we saw here, or we saw in, no, sorry, here, not in IDA. So these strings, so you can add those strings there, or you can use hexadecimal code. So for example, if you go here to the X view, you can actually look for these kind of patterns. So if you found a very specific decryption technique algorithm that was not implemented, or that is very particular or characteristic of a sample, you can just use those hexadecimal values as a signature, and it works. Okay, so you can use both, but in case of rank cost, this is very simple. So we just need to add some strings. So we are going to add regular strings. So how this thing works? So I'm going to say, okay, I want a rule. Wait. So string one. This string one will be, let's suppose, settings. Because we know that this sample needs settings, otherwise it won't decrypt the configuration. So the other one could be rank cost mutex. Could be rank cost mutex and eng, right? So next one. Let's add a third one just in case. I don't know, I'm going to add whatever. This is just like a very basic rule, just for you to understand how this will work. I don't know. Let's suppose updating file to C2C. I don't know. Updating file to C and C. Let's suppose we want those. So we have the strings. Now we're going to say the condition. The condition is basically a Boolean expression. So you can say any of those, all of those, only string one and not the other ones, or string one or string two and string three, stuff like that. So you can be crazy with that. You need, probably you should study a little bit about Jara rules, but those are great. So in this case, I'm going to say just all of them. So what I'm doing, this is a very basic rule. I'm doing just a rule I'm going to write this here. So it's going to call rankos. Yeah. Very simple rule. What I'm basically saying here is, Yara, please create a match if you find any file that has settings, rankos mutex ing, and updating file to C and C. That's the main idea. Super easy. And that's another thing very useful, because if you see a Java rule as an analyst, you understand directly, just looking at that, you understand what you're looking for, and also the system can understand that. Obviously, if you want to deploy this in a more like in a production environment, so you need to do some tests, you need to have like a bunch of samples related to rankos, a lot of samples that are not rankos, a lot of goodware with that, so you can see how many false positives you are getting and stuff like that. But for the sake of this workshop, we are going to keep this rule simple. That's it. So we are going to use CMD. Let's go to the desktop. We're going to use Jara. We're going to use Jara. Sorry, here I need to change the extension. Just yeah. Okay. Jara, and so wait. So we say Jara, we send the rule that we want to apply, and we say where we want to apply that. So that will be over desktop. So I'm going to copy this thing. Okay, perfect. So there are some files that couldn't be opened. Oh, but sorry. Okay, it captured our own Jara rule, so we need to fix the rule. Let me probably we need to change here. Yes. Okay, yeah, open. So we need to tweak a little bit the Jara rule, because it captures only our own Jara rule, not the actual binary. So there are some you will go to Jara, write Jara rules, Jara documentation, just in case, writing Jara rules. So you will see that you can append some types of strings. Probably that's the thing that is missing here. So for example, no case, white, ASCII white. So we're going to test that, those Jara rules. But we just need to test. But I have here. Okay, no. Let's test the. Let's start with. Let's think about this white. So we add here white. See if actually it makes sense. White. So it's a small modifier. We want rankos. Okay, so I always have this problem with the Jara. So I'm going to do some copy here. And I already have some Jara rules here, especially for Jara here for rankos. So the one that I have here actually is this one. And I don't know why it is not triggering, because it's the same thing. But so this, let's see, I don't know why this is not working. It should. So I'm going to pass the other Jara rule that I already have here. just in case, because I don't know why replace. Yeah. Do you want to reload? It's the same thing, but yeah, this is the Jara rule that previously created. I don't know why it is not. Yeah, I don't know what happened here, but if you see, the first Jara rule was kind of broken, so we ended up with where I copy the previous Jara rule that I already have, and that Jara rule was this. So just kind of, so this was the Jara rule. So probably I sent some strings that didn't work. But if you see here at this point, with this new Jara rule, that basically is what I told you. So I took all the strings, I add those some strings to this Jara rule. I find in my desktop 3 rencos. So we found rencos in the unpacked file, which is this one. We found another rencos in the suspicious.beam, which is this one that was the memory dump that I extracted directly after before writing before the malware wrote the new process memory. And also we found rencos in this one. Okay, so we found 3 Jara matches. That's nice. So last thing, so I'm going just to open this, continue this thing, just to show you a last stuff, last thing you can do with Jara. So we know that this malware is running in memory, so we can say, okay, Jara, I want to scan with Jara the PID, which is 6060, and actually it found that Frencos is running in this PID, right? So we solve the last this new question, which is how can I detect it? So it is, we can detect that with Jara. At least this detection of the Jara rule that we created is based on the unpacked sample, so we can detect unpacked samples, at least for Rencos, but if they are packed, we are not going to find any match, at least on disk. If the sample runs and it gets unpacked in memory, we are going to catch that sample in memory. So have that in mind. Now, last part, how can I automate this task? So we are going to see here, and well, the automation portion is more related to understand more about the things that are going on. So we know it is RC4. We know what is the data that is being decrypted, or at least where is it. But we don't know what is the key, and yeah, exactly all those details. So two ways to actually do that. So we know where all the decryption happens, but we need to we can just start like reversing this with all the opcodes and ECX and continue all this static analysis, but very in detail. But we can also do the same thing, but more dynamic. So we are going to help us with the debugger. So I'm going to take this unpacked sample. I'm going to send that to our debugger. And because I already know where the instructions, the interesting instructions are located, so I could add some breakpoints on those locations, and I could find the information I want. So remember, the information that is missing is which is the key, which is the actual data that is being decrypted, and that's it, because we already have the algorithm. So perfect. What we're going to do, we're going to the entry point, and we're going to have like on one side the IDA, and on the other side we're going to have the actual binary, the debugger. So we're going to have this, and we are going to press space to find the place, the address in which these interesting functions are located. So to find those functions in the debugger, so I'm going to press Ctrl G, like follow instruction, and I'm going to copy this instruction here. So this address. So I'm going just to this part. Perfect. And here, so I know that this function over here is the RC4 key wrapper. We know that the key algorithm or RC4 only does like the initialization. However, just for the sake of curiosity, so I'm very curious about these two arguments. Why? Because if you go to the RC4, especially the KSI algorithm, you will see that it receives the key and the length of the key. So the KSA algorithm contains that information. So if we study what this part receives, which are the arguments, probably we can get an idea of what's going on. So I'm going to add a breakpoint with, sorry, not here in the debugger. I'm going to add a breakpoint, so I know the breakpoint is here. I'm going to execute the sample, and here. Now I'm going to step into, so we are going to have align, both things align, step into, boom. So we have, there are two arguments here, and this is the function. So let's continue, step, 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 step. Okay. So we're going to see that we haven't entered this function, but we already have in the stack, we have two functions, two values. So in one, the first parameter is FB, the second is this thing. This thing seems to be more like an address. So if I click, right click and go to follow the word in dump, you will see, follow in dump. Sorry, is that? Wait. No, sorry, no, it's not that. So one is this one, the other one is this, the 21. So that is the one in the. Those were the two parameters pushed to the stack. So if I right click on the first one, so we are going to see that we have an address. This is like a buffer with information, and the other one is FB. So we know that the key is requires the key and the length of the key. Now, if we go here to the resource, just for curiosity, you will see something interesting. FB was the first byte, which is actually the one that is here, and the buffer that was sent as a parameter to the function and starts with 7D. This is 7D. Let's continue reading. 7D, E2, B8, both are the same, F5F. So it seems like this value is important. And the rest of the value contains something. So just, this is kind of experimenting, but at least from this point of view, I know that I need a key length and the key and the data of the key. So probably this value could be the key length. So, and from this part, it could start like the key up to the key length. So let's find where it finishes, FB. So probably, so it starts with FB. That probably could be the key length. The key could be this part, and the actual data could be this. It starts with C. How can we prove that? Really quickly. So what we're going to do, just we're going to go directly to the other routine, which is the RC4 decrypt. Why? Because it is the one that does the XOR. So if we follow the logic that we created here, the first value that must be XORed to return a valid value in the configuration must be CE. Sorry. So have that in mind. This is just an hypothesis, but all those hypotheses are really useful if you can speed up your analysis. So not every time you need to reverse everything, just if you want, but not every time you need to do it. So, okay, perfect. And actually, this kind of analysis is also super valid. So don't worry. So to test our hypothesis, we are going to add a new breakpoint specifically in this address, which is the XOR. And so it is 4037F. 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 We go there. And you see, this is the XOR. So according to our hypothesis, this is the key length, this is the key, and the first byte that must be XORed should be, or must be, sorry, CE. If that value is CE, probably we are in a good path. So I play, and let's look which are the values that are being XORed. The first one, which is the one that is stored in EXI, in ESI, is CE. Okay, nice. So let's continue proving our hypothesis. So the first one was this. The second one should be, or must be, BD. So play BD. Okay, so we can go on. The third one was E2. So E2. So yeah, it's done. We don't need to worry about anything else. The structure, the structure of the resource is actually this. The first byte is the key length. The rest of the array so contains the key actually up to the key length, and after that you will find the configuration. So solving the last question, how can I automate it? We already know the algorithm. We already know everything about the structure of the configuration. So we are going to write something very simple that is going to take the sample, is going to look for the resources, is going to extract the key and extract the information we want. And that's it. So that's why I added in your machine PyCharm, and we are going just to write a small structure. And just let's wait. So I already added some code. Close. I already added some code that is going to extract the settings resource. So you don't need to worry about that. You just need to worry about writing the actual Python configure structure, which is this. So again, wait, because it's kind of slow. Okay, so the first one, we say we're going to say, okay, resource is equals to, and I'm going to extract the resource from the file path. So which is the file path? I'm just going to copy at this point the malicious file, the rencos rat that I have. I'm going to copy it to my machine, here. Yeah, I want to copy as what? Kind of move. Probably this. Okay. Entonces, sorry, paste. And we're going to call it rancost. Okay, right. So we have a rancost.exe here. So we're going to say, okay, we're going to extract rancost.exe. With this, we're extracting the resource, same thing as we did here with resource hacker, but in Python. And now we need just to create like the mapping thing. So with the key length is equals to the resource blah And I told you, I got, where is it? Okay, right. Resource 0, that is the key length. The key, the actual key starts, where does it? It starts in the first, not in the second byte, which will be the resource 1 up to the top 1 to 1 plus key length. So will be, this will be resource 1 to 1 plus key length. Okay. So with that, we have covered the second section, which is this in blue. The third one, which is the data that will be extracted, it is basically, so will be 1 plus key length resource, something like resource. I want everything from starting from 1 plus key length to the end. So with that, we have said, okay, I want everything from this point to the end of the file. With that, so we have all the data. We already have the algorithm. So there is a library called arc4 in Python, arc4 in Python. So you can use it. So we are going to say just that config equals it says like arc4, and we pass here the key, the actual key that we need. And we say, okay, we are going to decrypt. What we are going to decrypt? We are going to decrypt the data and the output, because this thing is going to, we're going to get this output in a byte, as a byte structure in Python. I prefer to have it as a string. And I want to print the configuration and say, voila. So config and print magic. No, I don't know, like boom, to be more like wow. And wait, we're going to run the extractor. Boom. And you have the configuration. So we have the server, we have the password, the port that it was used. There are a lot of stuff going on here. You can start reversing like deeper into this, but the main point of this exercise was just to extract the configuration. So that is kind of the idea. That is how you can use malware analysis to speed up your analysis, because next time you find these kind of samples, actually you don't need to execute it. You need just to unpack it. You can use other services to unpack them, and you just need to send those samples to these kind of scripts, and you are going to extract the configuration without executing. So it is way faster. You know, if you see here, it's like 3 seconds and you have everything. And there is another thing, and that is probably if you send this to a sandbox, the sandbox is going to provide you this kind of information. But let's suppose the sample has, I don't know, like 4 C2 servers. So, and if the first C2 server is active on a sandbox analysis, probably the only C2 server that you will get is the first one, but you are going to lose the other 3. So have that in mind. And we are at this point we are good to go with the word theme. And just summarizing, I want to give you some other ideas. So we just go back from the word. Was amazing. I really enjoyed it. Hope you enjoyed as well. But the idea is not to do this manually. We did that just because we wanted to study, right? To learn new stuff. So the idea is to receive a feed of malicious files, automate something, and actually the automation could be a black box over there. An idea is to extract easily IOCs and TTP. because we did the analysis, we do have the TTP. So if you, with everything we saw here, we can create kind of a matrix, my attack matrix. So that will be great. But I have some ideas. So this kind of analysis can be focused on some ideas. First, you can track malware. So how can you do that? You can receive samples, send those samples to services such as Unpack.me, for example, or such as some sandboxes to extract the unpacked payload, add your configuration code, your config extraction code, and apply that code to the unpacked samples. Then, with all the configurations, you need to emulate the network traffic using a bot. So you can reverse the network traffic, build an emulator, and get everything. So how you can orchestrate this flow? Probably you can use Fame. This I added here the URL. Also, you can use assembly line. Really cool. But I have been used more Fame and more get used to that. So I really like it. I want to show you how an emulator works. And this is a working emulator for Catbug. Catbug is a banking malware. So I just reversed the whole thing, at least when we are talking about network traffic. And I'm just going to give you a demo really quick. So what I'm doing here is I'm actually speaking with some or talking to some Catbot C2 servers. Actually, this is the protocol Catbot uses. And if you see here, for example, when I get the binary, I actually get a MC, which, if you already know, this is a new update from the sample. This is a PE file that the C2 server provided me because my emulator was kind of behind of the current version. First thing, so you can use the botnets as your source of threat intel if you reverse those botnets. Second, for example, I'm going directly to the other really nice stuff that when I found it was like, oh my God, this is amazing. We can get all the modules, we can get updates, even the web injections, which is one of the hardest things to find in banking malware. And I mean, this is a real web injection just downloaded from the C2 server. Just in case, please block this Fortinet storage because it is being used currently as a C2 server for web injections. So this is an emulator for a botnet. This is the main idea that I want to show you here. So you can get malware samples, unpack them, extract configurations, and start emulating those to use the botnets as your feed. Then, if you want just to create a malware analyzer, you just use a feed of malware samples, unpack them using services such as Unpack.me, Integer, or even sandboxes. Unpack those, add your Java rules, add your extraction configuration modules. Again, you can use these same to services, and then all the information that you extract, send that information to your threat intel platform. Jerry means Threat Connect, whatever, but you will find that. Again, just like last things, you are not alone. So even though this can sound scary, there are a lot of projects that can help you with that. So for example, Cape Sandbox have a lot of malware configuration modules to extract and detect those samples. So at this point, you have an idea how to create that kind of modules. It is not easy, but you can help these kind of projects. Cape Sandbox has that capability. There is another one that is called malconf scan that allows you to scan memory forensic images, the memory forensic images, with this same kind of structure. So they have some modules and they can extract the whole thing. Also, there is another project that is called RAT decoders that have a bunch of stuff related to this config extraction. You will find in the wild more config extractions than network emulators, because every time you emulate something and you share with the community, the attackers are going to notice that and they are going to update the protocol. So have that in mind. Now, what is your motivation? If you are not sure after everything that I show you, so probably you can have more data. You can have another idea, and this could be this could give you more ideas. So if you are more like into this stuff of creating exploits and vulnerabilities, you can try that. For example, EmoCrash was a vulnerability found in Emotet, was a buffer overflow, and that was kind of a vaccine for Emotet, and that vaccine works from February to I think August. So this is another thing you can use. Also, there is this nice also talk, blog post in which a vaccine was created for Druidex exploiting a small flaw that the hashing routine, the API hashing routine has. It says Felipe Durate, but that's not me. That's a company of some of my friends, so that's great. That's another thing. Or also you can get a little more creative. For example, this was an example of someone that found an insecure protocol, at least in the Forfeits botnet, that was like some time ago, and they started to basically he registered a new domain that belongs to this botnet. He added a new PE file in that server, and basically Forfix didn't do any kind of verification. So basically, if the C2 server provides an antivirus, it will install an antivirus. So this guy did that. So it added there a binary that uninstalls Forfix from the computers. So kind of creative solutions, but based on the flaws of the malware. And lastly, will we win this war? Well, I'm not sure, but I 100% sure that this is the way to go. This is the way to actually fight this war, and this is the way to be not behind the attackers, but in front of them. Like always watching them. Like, okay, they are going to provide more information, or they are doing this new technique, so we have that data. And that's it. So questions. I'm open to questions, but over Slack, and that's it, guys. If you want to follow me, so you can follow me in Twitter, GitHub. Basically, is dark opcode. Remember, this is not a O, this is a 0. And that's it, guys. Hope you like it.